This is going on page 22 when we are done. And I will explain to you why it seems upside down, why it's on 22, all that stuff as we go along. Just trust me. Just stay with me here. But we're going to start up here above this line first. If I have a line that looks like that, is the slope positive or negative? Positive. All right. If I have a line that looks like that, then my slope is what? Negative. We should not ever get that stuff mixed up. We can't afford those kinds of mistakes. What is the slope of this line? 0. It's a horizontal line. The slope is 0. A vertical line. What is the slope? Undefined. Very good. We cannot afford to mess that stuff up either. Now, we also have to know which one is the y equals line and which one is the x equals line, which hopefully we all know, but sometimes some of us still get mixed up. So I'm going to show you something Ms. Ludicky showed me years ago, which I think is kind of genius. So, and you also have to know the difference between the words horizontal and vertical. Okay? So this horizontal line that has a slope of 0, if I write a lowercase cursive h, and I used to say, like you wrote, you know, like they taught you in elementary school, but they probably didn't actually teach you cursive. I don't know. It doesn't matter. Something looks like that. Then I want you to turn your paper upside down. And what does that look like? A y. So your horizontal, when I flip that around, is a y equals line. Don't ever mess that up again. Okay? Y and the h. Think about them together. Now, what if I take the x and I flip it upside down? What does that look like? An x. So that doesn't do any good. But if I cut it down the middle, it's a v for vertical. Okay? So x equals is vertical, y equals is horizontal. Those kinds of mistakes you cannot afford to make ever again. Okay, we got way too many other things to deal with. Everybody with me? Okay, so that's just a little tidbit in case you needed it there. All right, so let's talk about a mathematical relation that maps a set of input values to a set of output values. Okay, so inputs get mapped to outputs. That the phrase mapping, that might seem a little strange to you, may not have used those words before, but we're going to use them a lot. Input values to output values such that each input value is mapped to exactly one output value. So what is a relation that has its input values mapped to exactly one output value? What's that called? A function. Very good. So this is a function. Now, a lot of what we talk about today, words and stuff, should be familiar to you. That does not mean you should tune me out and be like, oh my God, I've been talking about functions forever. Because yeah, you have. But we are going to talk about things and look at things differently than you have before. And it's good that it's not brand new because it comes from a different part of your brain. It's not like I'm giving you all brand new information right now. We're just taking what we have and formalizing a lot of it. Formalizing the language and formalizing what we're looking at and stretching it beyond that. Okay? Now, for functions, in previous courses, you may have used the vertical line test. We even talked about it on Friday. It's not that the vertical line test is junk. It's good. We can still talk about it. And we use it to determine if it's a function or not. However, in AP Pre-Cal, we will use the statement, each input has exactly one output. If we have to state whether or not something is a function, we cannot say f is a function because f passes the vertical line test. That is not okay. We're not going to get credit for that. We have to talk about inputs and outputs. Okay, so we must connect inputs and outputs. Later in this course, we will learn why the vertical line test is not a valid explanation. So for right now, it's because I said so, and you're going to have to take my word for it. But then later on, we will talk about why that's not enough, even though it's been enough up until now. Because in Unit 3, we'll discover polar functions, and polar graphs often fail the vertical line test, but they are actually functions. So when we get there, we'll get there and we'll talk about it. Okay? Everybody good so far? Again, we can still talk about the vertical line test and see things that way. We just have to make sure we formalize our explanations when we're doing those. Okay. Next part here. The set of input values of a function is called the blank and represented by the blank variable. Well, my input values, are my input values independent or dependent? Independent. So that's what goes in this second blank. Independent. So the first blank is what that set of values is called. I'm going to try and lead you there without giving the answer away. But if I say that my set of input values is from 0 to infinity, that's my set of input. I also have a set of output. They have two different names. We always talk about them together. What's the input called? You've been doing it for years, so it's not a trick question. My y's represent the blank, and my x's represent the, what's the set of them? It starts with a D. I'll give you that. Domain, yes. Okay, the set of input values is called the domain. A little worried about that. Although, maybe you didn't know that's where I was trying to get you. I know, but I was trying not to just give it away. The set of output values is called the what? Range. And that would be dependent. Now, also domain and range, totally not brand new. Been doing that forever. But I'm always shocked and a little horrified when we start writing those intervals, how off the charts some of these things are. I don't even know what you're thinking when you're writing it down, because you can tell me things about it, and then when you try to write those intervals, I don't know what's happening in your brain. So hopefully we can minimize that stuff and we actually understand that, if how to write our intervals and whatnot. All right, so that's domain and range, and we'll come back to those things. Now, we're going to talk a lot about the functions, but then also their rate, how they change, and the rate of change, like we did yesterday. We talked about the fact that the height of the water was increasing the whole time, but the speed at which it increased would change, right? And so when we're looking at these things, you have to make sure you have it straight in your head, whether or not you are looking at the function or you are talking about the rate of change of the function, because those are two different things, and they can get things get kind of muddy when you get them confused in your brain. So if we're talking about the function itself, the graph that you can see or the equation, function f is positive when the graph of f flies above the x-axis or if the outputs are greater than 0. Hopefully that makes sense. Okay, we got an axis, x-axis, everything above the x-axis is positive. Everything below the x-axis is negative. But we are looking at the output values. Okay, that's what determines whether or not the function is positive or negative. So my function is negative if the graph lies below the x-axis or if the outputs are less than 0. Anytime we're trying to identify what's happening with the function, we're looking at the output values. What is happening with them? Are they increasing? Are they positive? What is happening there? So we talked on Friday about this function, f of x equals the square root of x. And I told you when we talked about it, we were going to pretend like we have no idea what it looks like, which for some of you might not have been pretending. I don't know. But we know that our domain cannot include any negative values, so I can't use any negative x values. And my outputs are not going to be any negative values either, which means that the function lives in the first quadrant. Okay? So the domain for this function, all the x values I get to use, I get to start at 0 and go to infinity. We are writing everything in interval notation. Do I ever get to include the infinities? I might put a bracket there. No, we never include the infinities, because infinity is not really a number, it's more of a concept. Because infinity plus infinity is infinity. And if you talk about infinity enough, your brain starts to hurt, and then you think you don't understand anything. So we won't go any farther than that. But you never include positive or negative infinity. So just don't even have to think about it. For this domain, would I include 0? Yes, okay, because the square root of 0 is 0. So there's my domain. And even though the entire thing lives in the first quadrant, if I want to talk about when the function is positive, it's positive between 0 and infinity. Never include infinity. Would I include 0 for this? No. Is 0 positive? No. Is it negative? No. So I don't include it. Okay? So be careful. Make sure when we're writing intervals for positive and negative that you are not including anything that's touching the x-axis, none of the zeros. Any questions at this point? Okay, so this is kind of an FYI for the course right here. The multiple representations, everything we do, we're going to look at the graphs, the equations, the tables, and how to write it verbally. So throughout this course, we'll learn to study the concepts of those four representations. Then, to be successful in AP Pre-Cal, you know, some students want to fight me the whole way. Fine, don't do it that way. Then fail the test. I don't know what to tell you. I don't make up these rules. So if you want to be successful in AP Pre-Cal, we need to be able to identify important information from each representation and construct equivalent representations. You'll hear those words a lot. Meaning that I've got the graph, I need to make an equation, or I've got a table, I need to make a graph, or whatever. So this may sound scary or confusing, but we'll have lots of opportunities to practice, and eventually it'll just kind of become second nature to you. Unless you fight me the whole way, right? I can only do so much. You got to do also. All right, flip this over. I know it looks upside down. We'll talk about that in a minute. But here's a base question. Why we did what we did yesterday first to hopefully make this make a little bit more sense. So this says the figure shows an empty vase. At time t equals 0, water begins pouring into the vase at a constant rate until it is full. Which of the following could depict this situation where time in seconds is the independent variable and the height of the water in the vase in inches is the dependent variable? All right, so before we worry about what the right answer is, let's look at these graphs and decide if there's anything we know for sure it isn't. Why do I know for sure it's not? Okay, I heard A and C. Let's talk about A first since I'm over here. So A, it can't be A. If my answer was A, what would the vase look like? A cylinder, okay, because that would just be constant the whole time. Okay, good. And then I heard no to C. Why not C? Yeah, because there wasn't a hole in the container, right? Can't be C because the height is increasing, then the height is decreasing. Well, our height doesn't get to decrease at any point, so it can't be C. Now we've got B and D, and we don't have to overanalyze A and C at all. So don't tell me out loud, but come up with what you think the answer is. We're going to write a whole bunch of stuff before we talk about what the answer is anyway. But go ahead and think about what we did yesterday. See if you can make sense of it. Looks to me like a change happens right about there. Okay. So we're going to talk about the diameter of the vase, or, you know, how it's getting wider and skinnier. So when I start here, when I'm starting here, as I get up to here, my diameter is increasing. So in this bottom part, we're going to put diameter is increasing, and I'm going to abbreviate increasing I and C period. We get to abbreviate a lot of things that make sense, but there's some things that you would think we should be able to abbreviate, and we're not allowed to. Again, not my rules. I want you to get the points. Okay, so I'll just make sure you know how to write things and not let you get away with things that you shouldn't be doing. All right, then we're going to put these little 3 dots like this. Anybody know what that means? I rarely find anybody that does. I'm just always curious. What? What do these little 3 dots mean? It's a symbol. Do we know? Okay. So these little 3 dots, this is going to be a lifesaver for us. That means therefore. That's a big word that we're not even abbreviating. We're using a little symbol for, but we'll use it a lot. Little 3 dots just means therefore. So diameter is increasing. Therefore, the height of the water, here's what I know the height of the water. I know that the height of the water, well, the height of the water is increasing no matter what, right? The height of the water is getting increasing. I don't care how big or small that diameter is. Are things speeding up or slowing down in that section? Slowing down. So the height of the water is increasing at a decreasing rate. Okay? The height of the water is increasing at a decreasing rate because it's getting wider. Does that make sense to you? All right, so now this part over here, when I go from the pink line up, the diameter is decreasing. Therefore, height of, oops, that's not all one word. Height of water, height of the water is still increasing. I should have said is increasing at, are things speeding up or slowing down? Speeding up at an increasing rate. Okay, so my function is increasing for this part at a decreasing rate, and for that part, an increasing rate. And it should say height of water is, there should be an is in here, increasing. Sometimes I leave words out, like your sentences don't have to be perfect, but they should at least make sense. All right, so knowing all that then, have we made a decision between B and D? What do we think it is? D. So my height's increasing no matter what. It starts to slow down and then it speeds back up. Okay? And the answer is D. Okay. What questions do we have? Anything? Do you think yesterday's activity helped this a little bit? Okay, I hope so, because we can at least get one question on the AP test right? We was our first lesson, so we're good. Okay. Let's look at this graphical behavior of functions. Now remember, when we are identifying things about the function, we will also talk about the rate of change. But when we're talking about the function, if we have a graph, we can look at it. So we won't always have a graph, but we can look at it and we're looking at what's happening to the output values. So if my graph is increasing, then what this says is as the input values increase, so my inputs, my x values, they increase no matter what, because we always go left to right. So I'm going left to right no matter what. But as I go from left to right, my output values are getting bigger. That's what makes the function increasing. Does that make sense to you? Now, increasing and decreasing parts of the function, that may be something that you've already talked about, but I know there's some other stuff in here that you haven't. So again, for this one, as x increases, as my input values go from left to right, my output values are getting smaller. That means the function itself is decreasing. So no matter what, input is increasing, and then we decide what's happening with the output. Okay? And both of these say always increase or always decrease. That's because these are linear. When I get to this one, we'll get to concavity in a minute, but this function is decreasing, then it's increasing. So it obviously can change. It's not like it's always an always thing. Okay? Increasing and decreasing make sense? Can I identify those? All right. Then concavity. Concave up. Visually, it's up like a cup and down like a frown, right? But mathematically, it's concave up because the rate of change is increasing. And it's concave down because the rate of change is decreasing. Let's talk about how that works. So these rates of change are constant. They're the kind of rate of change you already understand fully. But we understood, from the water and everything that rate of change can change. So the rate of change of this, that kind of looks like a parabola, but we don't know if that's what it is, but it has that shape. If I would look for a rate of change at a single point, because the rate of change at that point is different than the rate of change at the point right next to it and the point right next to it. So we start to look for rate of change at a point. For us to actually find that requires calculus. So I'm not going to be able to tell you the rate of change is blah, blah, blah. But we talk a lot about the rate of change anyway. So we think about having, if I actually had little lines here, like if I could actually put little lines that would just touch at a point, we'll talk about those a little bit more in a couple days, something like that. So I can talk about the slope in general, because I understand slopes of lines. You can also use your pencil here. So I've got is this slope positive or negative? Negative. So my slope is negative. As I go along the curve, then it's 0, right? Then it becomes positive. So if my slope is negative, then 0, then positive, clearly the rate of change is increasing, because that's how you go from negative to 0 to positive, right? If I do the same thing here and think about these little lines and use my pencil, this rate of change is positive. It's positive, 0, and then negative. So that's what makes the rate of change decreasing and why it's connected to concave down. Okay? Any questions at all? All right, now, we don't have to overanalyze the rates and use the pencil all the time. Sometimes it helps to wrap our mind around things, but here's something that's going to help a lot, and we are going to write this a lot as the year goes down. It's called the fun chart. So write a lowercase f, then it's going to look like the word fun, but it's not actually a U and an N. It's a concave up, concave down, like little parabolas. So up and then down. See how it looks like fun? That's why we call it the fun chart. Then after that, we're going to do arrow up, down. So it's up, down, up, down. Then we have a second row. In calculus, you get a third row, okay, but we only get 2 rows. Under the F, capital R, that's for rate of change. We skip the concavity stuff and start with the arrows, up, down, and then plus, minus. So up, down, up, down, up, down, up, down, plus, minus. Okay, that's your fun chart. We're going to write that a bazillion times because we want to be able to circle and underline and do things like that, all right? Here's what this means. If I look at my function, I can see if my function is concave up, then the rate of change is increasing. That's what that says right here. If my function is concave down, rate of change is decreasing. Even though we know by looking at this right here, the function itself is decreasing right here, right? Since the function is decreasing, the rate of change is negative. Here, the function is increasing. Since the function is increasing, the rate of change is positive. Okay? Because we don't always have a graph to look at. We sometimes will, what if I said, hey, I am telling you, your rate of change is positive, so what's happening to your function? Well, when the rate of change is positive, my function is increasing. Okay, you see how that works? This is a lifesaver, I'm telling you. And we'll get to a lot of times where I go, what do you think we need? And somebody will go, fun chart. We write it down and it helps everything easier, okay? So we write it, every time you need it, write it down. Don't just go look at something, because that should definitely be something you learn. You're just writing it in your sleep. You don't even think about it anymore. You just jot it down and boom, you're done, okay? Questions? Right, fun chart to save the day for sure. All right, so before we move ahead, it's important that we clarify a few things about notation and vocabulary. Those things are huge. First, when describing features on the graph, like increasing, decreasing, whatever, we generally write intervals to explain them, and we always use the input variable when writing intervals. So when we look at decreasing, we are looking at the output values decreasing. We talk about Y, we write about X. The only time you will write an interval of Y values is if they're asking you for the range. Everything else, we're writing intervals of the X values. Okay? Does that make sense? We're going to get to that in just a second. All right, so I want you to take this piece of paper, and you're not going to fold it in half-half. You're going to fold it so that it goes right to that line and you can still see the title. So it's like almost in half. Then you'll understand a little bit better in just a second why this is upside down. Because when we put this in your ISN, and we'll do that at the end, so I tell you how to do it right, when you tape it down and you're trying to look at your notes and it's taped up here, then you can flip it up and your notes aren't upside down. Okay? So we'll get there in just a second. So just fold it, and I'm going to hand out the second page of what we're doing. If y'all could just take this and pass it straight back, because it's hard for me to get there. Y'all's are coming from right there. Here, I'm just going to give those. If y'all will have extra, just leave them on the table, just in case I didn't count right. Okie dokie. So this second piece of paper, which is 2 of 3, so tomorrow you'll get the third one. This is also going on page 22. I'll explain to you how that works when we're ready to have that explained. Okay? All right. So, example 2. The figure shows the graph of the piecewise function f over the interval from 0 to 9. This is written in inequality notation. We are not writing anything in inequality notation, but we have to be able to read it. It could be either given to us in inequality or in interval, but we're writing everything in interval notation. This statement in interval notation looks like this. Not always, but sometimes when it's inequality, I change it to interval because it makes more sense for what we're doing. But, that's just kind of a personal preference there. All right, so it says, what are all the intervals where the graph of f is increasing? Not the rate of change, but the graph. And this says this is a piecewise function. So let's talk about that term real quick. For some of the crazy curves we see, some of those are just one equation, no big deal. This I can't write with just one simple equation. It's actually pieces of 3 different lines. Then we would restrict the domain, and that's how you get the piecewise function. The fact that it's a piecewise function really is kind of irrelevant here, so we don't have to focus on it. But take your pencil and mark over where the graph of f is increasing. Let's go ahead and make a little mark over. It's increasing here and here. Would you agree with that? Because x is going from left to right no matter what, and the outputs are increasing there. So now we need to write the intervals. Remember, we are talking about what's happening to y. Y is increasing. We are writing about x. So this starts down here at -2. I don't care. That -2 has nothing to do with anything. All right? So I'm going to I actually start at 0. Starting at 0, and I go to 3. So from 0 to 3. Now, at 3, right here, is the function increasing or decreasing? At 3? Oh, yeah, it's kind of, we don't know what's happening, right? It's where it's changing. So when we write intervals of increasing and decreasing, we leave them open no matter what. Okay? Then I have a second interval, so I got to union that. And what's that next one going to be? 7 to 9. Good. Okay. What questions do you have? Are these ordered pairs that I get to go plot? No, they're intervals, right? We need to understand interval notation. Say that one more time. Yes, because all it says is, where is it increasing? Since that's what it's asking me. If it asks me for both, then I could say it's increasing here and it's decreasing on the other, but it just asks me for intervals of increasing. Okay, good question. Anything else? All right. So the second thing that needs to be clarified is the phrase rate of change. What's another way to say rate of change? Slope. Okay. This phrase will be utilized repeatedly throughout this course and AP Calculus. We talk a lot about rate of change in both of these courses. It's important to understand the meaning. Essentially, rate of change simply means slope. Anytime we see the phrase, we can replace it with slope. But when we write about something, we don't say slope. We would say rate of change. And unfortunately, rate of change is one of those things we're not allowed to abbreviate, which you can in calculus, you can't in pre-cal. Again, I don't know. I don't make the rules. I just want you to get the points. So we got to write it out, but it won't kill you, I promise. Haven't lost a single student to that. This is important for y'all because I know a lot of y'all don't read your directions very carefully or anything very carefully, but you must read very carefully in this course because stating that F is increasing is very different than stating that the rate of change of F is increasing. So that's what I'm talking about when you say, is it increasing? I'm like, what is it? What are we talking about? Are we talking about the function? Are we talking about the rate of change of the function? Because those are two different things. They can both have the same answer depending on the graph, but they're two completely different concepts. All right, so let's look at these graphs. We've got the graph of F here. And when it says the F, we're talking about the graph itself. F is positive. See, all these output values are all positive. They're all above the x-axis. So all positive because outputs are all positive. Hopefully, identifying that visually makes sense. Then F, the function, is decreasing because when I go from left to right, the output values are getting smaller, So because the outputs decrease as the inputs increase. That's a function property. Then when we talk about the rate of change of f, even though the function is decreasing, the rate of change is increasing because the graph is concave up. Okay. Now I could use my pencil and go, all right, well, this is negative, then it would like become 0, so I can see that it's increasing, but you need to tie it to concavity, because if we're going to explain ourselves in words, we have to talk about concavity. So let's write the fun chart again. We'll write that down. You'll get really good at it. We'll write it really fast. So if I want to know about the rate of change, the function is concave up, so the rate of change is increasing. The function is decreasing, so what does that tell me about the rate of change? It's negative, right? Everybody good with the fun chart and how that works? We're going to use it a lot, so everybody good? All right. Then here's G. G looks to me like it is negative because all of the output values are below the x-axis. G also looks to me like it's increasing because as we go from left to right, the output values are getting bigger. We agree with that? So the function itself is negative and the function itself is increasing. The rate of change of G, is this concave up or down? Down. Since G is concave down, the rate of change is what? Decreasing. Decreasing. And the function is increasing, so that means the rate of change is positive. So the function is negative, rate of change is positive, and decreasing. Okay. If you try to overanalyze that and go, but it doesn't make sense if just go with the fun chart, because that's where you get lost in your own brain and your own thoughts. Okay, we good with that? Questions? All right, flip it over. Let's go ahead and look at this one. So example 3. This graph right here with the numbers missing, you will see something exactly like that on FRQ3. No, and it'll have to do with trig. We're not talking about trig right now, but we're still looking at these graphs, and we can answer a question that's going to be asked on your AP exam. We'll have 2 right by now. So it says the graph of h of t and its dashed midline, don't know what that is yet, don't worry, doesn't matter, for 2 full cycles is shown. F, G, J, K, and P are labeled on the graph. No scale is indicated, no axes are presented. The t coordinate of F is T1, so I'm starting at F. This is T1. And the t coordinate of G is T2. So when it says this, that's an interval from T1 to T2. That just means I'm looking at that part of the graph. This says, on this interval, which of the following is true about H? Does that mention anything about rate of change? No. So that means if I'm not talking about rate of change, I don't think about the fun chart at all. I'm looking at the graph. Is that part of the function positive or negative? And what do we look at to determine that? Do we look at the inputs or the outputs? Outputs. Inputs are increasing no matter what. The outputs are 4 and 0. So on that part right there, is that function positive or negative? Positive, because we don't include 0. It's not a trick or anything. So that means I can eliminate C and D, because the function is positive. Is the function increasing or decreasing? Decreasing. So my answer is B. Okay? What questions do you have? All right, we're going to pause there for today.